Hi, my name is Anwar Hamzah. Today, my groupmate and I will be presenting our asset integrity and risk management project. So the equipment that is assigned to us by Dr. Ainul is reactor, or to be more specific, chemical reactor. So in this project, we will present the FMEA for chemical reactor. Our group consists of the 5 members and it is listed as you can see on the slide.
Hi, my name is Muhammad Zulfati bin Muhammad Zaki. So this is the presentation outline for our group. We will be discussing on the introduction, literature review, methodology, result and discussion, and also the conclusion.
Hi, my name is Anwar Hamzah. Today I will be presenting on background of study. So when talking about chemical reactor is essentially an equipment used to contain the controlled chemical reaction of something if you wanted to create a product or something in a plant. And when talking about containing the reaction, it does not only include the vessel in which the reaction occurs, it also includes important components, and these important components is illustrated on the picture on the right of the slide. As you can see, it is an example of a chemical reactor. And chemical reactor is used in various industries such as petrochemical, pharmaceutical and chemical. It is used to create intermediate or the final product of a target product for the plant. So when dealing with chemical reactor, reliability and integrity are important as failure can lead to a detrimental consequences. An example of this is the Flixboro accident in 1974, where a rupture of a piping used to bypass a chemical reactor resulted in an explosion. The explosion consequently killed 28 workers. So one of the way to assess the risk or to control or to avoid such thing occur is a method called FMEA, and FMEA is a risk assessment tool. And the main point of FMEA is to create a scenario or to create a preventative measure rather than reactive measure. So when dealing with FMEA, there are 3 main variables, which are severity, occurrence and detection. These 3 variables is used to calculate risk priority number. This will be explained by my other members in more detail as we enter the literature review.
Okay, for the next part, we have the problem statement. So as all we know, chemical reactor is used to contain all the chemicals that are needed for a reaction. So inside the reactor, if there is any failure, it can lead to severe consequences. So it gives us the next problem, which is we need to find an effective preventive maintenance, which are very needed in order to detect all the possible failure are needed. So from that, we can identify the objective of our project, which is to identify the potential failure mode of the chemical reactor. And the second objective is to develop a corrective and preventive action for each failure. By using these 2 objectives, we can gain all the information that we need in order to prevent all the possible cases that can occur during a chemical reaction on a chemical reactor.
So the function of the reactor. Chemical reactions within the chemical, petrochemical and oil industries are executed within specialized equipment known as reactors. A widely accepted concept is that it refers to any vessels utilized in converting raw materials into desired products, which is a fundamental unit operation in the analysis of chemical processes. Typically, a chemical reactor must be capable of fulfilling a minimum of 3 functions, which is the first one is providing sufficient residence time for the reactants to complete the chemical reactions, facilitating the necessary heat exchange, and also enabling the phases to come into close contact to aid the reactions. The working principle of the reactor in the oil and gas industry involves the introduction of reactants into the reactor vessels, which is typically designed to withstand high temperatures and pressures. When inside the reactor, the reactants undergo chemical reactions that result in the production of the desired products. Regardless of the design, a reactor must offer adequate time for the chemical reactions to occur, as well as efficient heat transfer to maintain the desired reaction temperature. Once the reaction is complete, the products are separated from any unreacted materials and pass through various downstream processes for further purification, refining, or transportation.
There are four commonly used standards in the fabrication of a chemical reactor. First is ASME boiler and pressure vessel code, which will provide guidelines for the material selection, construction, testing and certification to ensure safe and reliable operation. Second is API Standard 620 to cover the requirement for materials, design, fabrication, inspection, testing and also certification of tanks used for the chemicals. Third is ASTM International Standards to provide specifications for the material used in the reactor fabrication, including the mechanical properties, chemical composition and also manufacturing processes. Lastly is OSHA Standard 19110.119 require the employer to develop and implement safety program to prevent or mitigate the consequences of catastrophic chemical release.
For the method of inspection of this project, we have seven types of inspection that we will be using. The first one is the visual inspection, which is a non-destructive method involve human vision to detect the defects. The second one is the ultrasonic testing, using a high frequency sound wave to detect flaws in the material itself without having to search physically. And the next one is radiographic testing, which uses X-ray or gamma ray to penetrate thick object to find the defects. It uses on a large tank or a chemical tank or any tank that are not possible using ultrasonic or visual inspection. The fourth one is using liquid penetrant solution. Using this liquid penetrant solution, it can find a surface breaking defects, which the dye itself will show the color of the cracks in on the surface area. So the fifth one is the magnetic particle inspection. It uses a ferromagnetic elements, which use to detect surface or near surface defects. And the sixth one is the eddy current testing, and it uses a EM electromagnetic induction, and the heat that is produced in the material can provide a thermal images of the defects. And the last one is the pressure test. It functions by pressurize the component, and we can find the integrity of the component from its pressure retain capability. And that's it for the method of inspection. We move on to the next part.
For the failure incident related, the first case is from the record of incident that occurred in the range of the year 1962 and 1987 in the United Kingdom. There were 189 incidents that happened regarding to chemical reactors, and out of 189 incidents, only 134 incidents were successfully classified. The type of process that the reactor were going through was ranked as the one with the most incident occurred to the least, and it's apparent that polymerization reaction have the highest percentage of incidents occurrence, which are followed by nitration, hydrolysis and sulfation. The prime cause of this incident have been identified and can be classified into two types. First one is the process chemistry. The product mixture decomposed. Second one is unstable and shock sensitive byproducts were produced. Third one is unintended oxidation occurred. For the second cause is on the plant design and operation, where there might be loss of cooling water, too rapid heating at the reaction initiation, and operator failed to follow written instruction. Another incident happened on October 8, 1973 in Ichihara, Chiba, Japan. The incident that happened was an explosion due to the mishandling of only one remote control of valve separated from atmosphere in the polymerization reactor at a polypropylene manufacturing plant. In short, the cause of the incident is the outlet size of the remote shut-off valve of the number 6 polymerization reactor, which was accidentally opened instead of number 4 reactor. There was a propylene leak and a considerable volume of propylene vapor dispersed across the manufacturing site. There is an electric spark in the pelletization factory, and it has caused ignition resulting in a large-scale gas explosion. In the effort of avoiding this incident, a countermeasure plan was created. The following things are considered as preventive action against the recurrence. First one is the illumination on the panel must be kept on even if the power goes off. Second one is the panel board switches must be set such that they are not misused when only one valve separate from the atmosphere. A blind plate must be placed. A lock must be installed so that the valve cannot be easily opened, especially during maintenance.
So next, I'm going to talk about the boundary of equipment. Before I delve any further, I would like to emphasize that our study or our project focuses on two main type of chemical reactor. The first one is continuously stirred tank reactor, CSTR, and the second one is plug flow reactor, PFR. So when talking about equipment boundary, the Center for Chemical Process Safety defined equipment boundary as the demarcation of equipment defining components. So for the case of CSTR, we decided that the boundary would be agitator, inlet feed, pressure relief device, and lastly cooling jacket. And for the plug flow reactor, the approach is not as direct as CSTR because PFR is used to describe a reactor model of a cylindrical tube. So when we discussed, we decided to treat it as a pressure vessel. So based on that, we follow the ASME BPVC geometric boundary of a PV, which is as stated at the slide: pressure retaining surface and opening such as manhole, and the attachment welding to pressure retaining surface and external connection. So when we do FMEA to capture the PFR model, we only include the pressure retaining surface and inlet feed, and therefore that is our boundary condition for PFR, which is the shell or the pressure retaining surface and the inlet feed for the equipment.
For the methodology for designing FMEA, the first step should be defining the scope and boundaries of the chemical reactor, its purpose and the system it operates in. Besides that, we also need to determine the component or subsystem that will include in the analysis. Next step is we have to come up with the design or process details, where we specify the chemical reactor process flow, including all equipments, inputs and outputs. Once everything has been specified, we have to brainstorm on all possibilities in which the reactor could fail and malfunction, including giving rating on severity, likelihood of occurrence and detectability. And then we can proceed on calculating the value of RPN. If the value of RPN is low, then it means that the design or the process is reliable. Thus, we have low priority of assessment. If the value of RPN value is high, then it is prone to failure. Thus, we need to come up with corrective action and go through the design process detail all over again, so that we can make improvement on the process and maybe adding countermeasures to reduce the value of RPN that will lower the risk of failure.
So for the FMEA of the plug flow reactor or PV, PV is a device that functions to contains the reactants and internal pressure. The highest RPN for PV is the rupture of the retaining surface and the lost primary containment. The potential cause are the corrosive environments, oxidation and formation of metal inclusion. The potential failure mode is the internal corrosion of the pressure retaining surface. Current process control is the regular ultrasonic testing. The severity is 9, occurrence is 7 and the detection is 4. The recommended action is to record the corrosion rate and monitor wall thickness, which is to be performed by the mechanical static and corrosion engineers. After the action is taken, the severity is down to 9, occurrence 3 and the detection is 4. The RPN is lowered down from 252 to 108.
For the next FMEA that we're going to talk about is about the cooling jacket. So what we all know, cooling jacket is used to perform cooling process in the reactor internal during a chemical reaction. So we have seen that the most highest prone of failure is inside the pump mechanical failure itself, because what is the potential effect of this failure is that it will be unable to pump the cooling fluid inside the cooling jacket itself. And we've seen that the potential cause of this issue is that the motor itself is having a failure, or the impeller of the motor is damaged, and we might have to see deeper inside that later, or the blockage inside the pump inlet itself. So what we have done now is use a backup pump and using bypass line. From this, we can continue the process without having to stop the production of that reaction, of that chemical. So the severance of this issue will be score of 9 and the occurrence is 4. And the detection itself will be we have a score of 7. And the total RPN that we get from this is 252, which is the highest among all the others. So what are the recommended maintenance procedure that will be done is to perform maintenance and also inspection. From that, we can see whether it needs to be repaired or be replaced with refurbished equipment. and the issue is scheduled to done by 18th of April, and the score of the severance, occurrence, and detection will have the score of 615 with a total of RPN 30. So we have seen that by figuring out this early failure, we can reduce the RPN score a very large amount. So this is what so that's why we are using the FMA table to compare which are the most important things that we need to be done right now.
This is the FMEA table for agitator of the reactor. There are 5 potential failure modes, which are blade failure, shaft bending, bearing failure, motor failure, and agitator failure. Among these 5 failure modes, the highest risk priority number RPN is the blade failure. The process involved is agitator blades. The effect is causing the incomplete mixing of the chemical in the reactor. The potential cause is due to fatigue and corrosion. The current process control is by routine maintenance. As for action, the recommended action is to make regular inspection and replacement of the blade. This action should be taken by the maintenance team. The RPN reduced from 384 to 270 after the action is taken.
For the FMEA of inlet feed, we have identified the process function, potential failure mode, potential effect of failure, and given rating for severity, likelihood of recurrence, and detectability, which then proceeded to calculating the RPN. The RPN value for all the process functions are quite high, therefore we suggested the recommended action as countermeasures. For example, in the process function of delivering feedstock with consistent quality and purity to the reactor, potential failure mode that could happen is that there might be contamination of the inlet feed with impurities. Potential effect of failure will be reduced reaction efficiency, catalyst poisoning, and corrosion of reactor components. And the calculated value of RPN is 280. Therefore, we have to come up with countermeasures of doing regular sampling and testing in order to ensure that it meets the quality standards. And the action taken to ensure the success of the countermeasure is by installing filtration system and automated sampling system to make the regular sampling routine much easier.
So we go for the FMEA of the PRV or pressure relief device. So PRV is a device that functions to release the excess pressure from the reactor vessel. The highest RPN for PRV is the leakage of the PRV itself. The potential cause is the corrosion or damage to valve components. The potential effect is the escalation of reactor contents into the environment. Current process control is the regular inspection and maintenance. The severity is 9, occurrence is 3, and the detection is 5. The recommended action is to replace corroded or damaged components and increase maintenance frequency, which is to be performed by the maintenance and corrosion engineers. After the actions taken, the severity is down to 4, occurrence is 1, and the detection is 8. The RPN is also lowered from 180 to 32.
So in conclusion, by using FMEA, we can identify and mitigate the hazards related to chemical reactor safety. The effective mitigation strategies also can be developed to improve the safety and efficiency of the reactor. By doing so, the communication among the reactor stakeholders can be improved, which the reduce in likelihood of accident can promote the safety culture.